All right. Hey, we're live. Okay, cool. All right. So the last thing we talked about last week was entropy, and we remember that entropy is chaos or randomness, and a universe likes things to become more random, more chaotic. So when we tend towards thermodynamically favored or tending towards spontaneity, then we say a positive delta S, which is an increase in entropy, tends to be thermodynamically favored. And the last thing I left you with was discussions of both entropy and enthalpy are used together in combination to determine if a system is thermodynamically favored. If you have an entropy that is thermodynamically favored, and you have an enthalpy that is thermodynamically favored, your system will be thermodynamically favored. If you have an entropy that is not thermodynamically favored, or thermodynamically unfavored, or not tending towards spontaneity, and you have an enthalpy that is also not thermodynamically favored, your system will not be thermodynamically favored. Make sense so far? So there's two terms, the entropy and the enthalpy, chaos and heat. When they work together, they determine if the system is thermodynamically favored or not. If they're both thermodynamically favored, the system will be thermodynamically favored. If they're both thermodynamically unfavored, the system will be thermodynamically unfavored. What happens if the enthalpy is thermodynamically favored and the entropy is thermodynamically unfavored? Or conversely, if the enthalpy is thermodynamically unfavored and the entropy is thermodynamically favored? What happens if they're in conflict? And that's what we're going to talk about today. So first and foremost, the thermodynamically favored systems are a negative enthalpy, a system that releases heat, and a positive entropy, a system that becomes more chaotic. Think of explosions. Explosions, like fireworks, are the ultimate thermodynamically favored process. They release a lot of heat, and they spray their chemicals all over the place, and what used to be a little bit of solid becomes a whole bunch of gas. It's a very thermodynamically favored system. The universe loves fireworks. The universe's favorite day is July 4th, second only to December 31st. And then whatever Saturday night my redneck neighbors are setting off fireworks. I live in Henderson. Yeah.
So thermodynamically favored is endothermic or exothermic?
Exothermic. The universe wants its energy back, and it also wants to make things more chaotic. Okay. If you're comfortable with that concept, give me a thumbs up. If there's anything about that concept that's confusing, wave your hand around. Okay. Again, spontaneity is just a fancy way of saying thermodynamically favored. And the reason I keep saying thermodynamically favored is for the handful of you who are taking chemistry AP, that's what the AP graders like to read. By the way, the AP test is in 3 hours. Yay! That's why the AP kids get breakfast. Okay, so the value that we put together is called free energy, and it's named for this guy named James Willard Gibbs. American. So we have it gets the letter G because of Gibbs free energy. And the idea is entropy and enthalpy are working together to create a single value called free energy. Now, sometimes the enthalpy and the entropy are both thermodynamically favored, so the free energy value will be thermodynamically favored. Sometimes the enthalpy and entropy are thermodynamically unfavored, making the free energy value thermodynamically unfavored. And sometimes they're in conflict with each other. When they're in conflict with each other, temperature determines which one is bigger, which one wins, if you will. Temperature determines how big either entropy or enthalpy is. Which one do you think has a greater, which one do you think upon which has the greater effect of temperature? You think temperature affects entropy better or enthalpy better?
Enthalpy.
Ben, you're right. Why do you say entropy? Remember, entropy is molecular movement and molecular chaos. Temperature determines how fast molecules move. The faster they move, the more chaos there is. Would you like to babysit 2 sleeping kids or 2 kids that just ate ice cream? The sleeping kids, right? Because they're going to stay put. So molecules work the same way. So the free energy formula is this. Delta G equals delta H minus T delta S. Temperature directly affects the entropy because temperature is a measure of molecular movement. The more molecular movement you have, the more entropy you have. Right. So, 2 big things to pick up here. First and foremost, because physics also uses entropy, entropy will always have the units of joules per mole Kelvin. In order to make the units work, you have to first take your entropy value and turn them into kilojoules. If a unit becomes larger, the number must get smaller. So how many joules are in a kilojoule? 1,000. So if the unit from joules to kilojoules is getting larger, the number must get smaller. So you take your joule value and you divide by 1,000. If that is clear to you, give me a thumbs up. If that is unclear, wave your hand around so I can say it again. Okay.
So
1 then 2. You're good?
Yeah.
Okay. Yeah.
So entropy is the only one in kilojoules.
No. Entropy will be given to you in joules per mole Kelvin. You need to divide it by 1,000 to get to kilojoules per mole Kelvin.
Okay, yeah.
All right, so here's how it works. If your, temperature must be, is the other part of the 2, temperature always must be in what unit?
Kelvin.
Kelvin. When we put into a formula, temperature must be in Kelvin. Are there negative kelvins?
No.
No. So Kelvin, temperature, will always be positive. Temperature is always going to be arithmetically positive no matter what. All right. If our entropy is thermodynamically favored, what sign will the entropy have? It is thermodynamically favored.
And entropy, that's positive.
Positive. So the universe likes when the entropy gets larger, becomes more chaotic. For a thermodynamically, I'm going to write this, thermodynamically favored. For a thermodynamically favored enthalpy, what sign will that have? Negative. The universe likes systems that release their heat. Arithmetically, a negative minus a positive will always be what? Negative. Arithmetically, a negative minus a positive will always be negative. Remember that math thing that you learned back in 7th grade?
Yeah.
Positives and negatives? Is that clear? Now, let's look at the other side. A thermodynamically unfavored entropy has what sign? Makes it easier now. Negative. And a thermodynamically unfavored enthalpy has what sign? Positive. Can you agree that positive times a negative is negative? Oh, yes?
Yeah.
Okay. So, a positive minus a negative will always be positive. So far, so good?
Yeah.
Okay. Now, where things get dicey is when the entropy is thermodynamically unfavored and the enthalpy is thermodynamically favored, or the entropy is thermodynamically favored and the enthalpy is thermodynamically unfavored. Make sense so far?
Yeah.
Now, when that happens, it is the temperature that will determine which one is bigger. So in this case, if the entropy is thermodynamically favored, then this is going to be thermodynamically favored at low or high temps. Why don't you take a second and ask your neighbor. So if you have a thermodynamically favored enthalpy and a thermodynamically unfavored entropy, is this going to be thermodynamically favored at high temps or low temps? Take 10 seconds.
Oh, really? Yeah. I think just look it up. How do you chemistry next year?
All right. In this first case, we're going to vote here with our hands. Make sure everybody's got a hand. If your entropy is thermodynamically unfavored and your enthalpy is thermodynamically favored, if you believe it is thermodynamically favored at high temperatures, raise your hand. If you believe it is thermodynamically favored at low temperatures, raise your hand. You are correct. Because at low temperatures, your thermodynamically favored term gets very small. Low temperatures. Okay? Because at low temperatures, the entropy term gets small and the enthalpy term takes over. And the opposite's, of course, also true. If you have a thermodynamically favored entropy and a thermodynamically unfavored enthalpy, this is going to be thermodynamically favored at high temperatures. Because at high temperatures, the entropy term is going to get bigger. Temperature determines how big the entropy term will be and whether the system is entropy driven or enthalpy driven. How are we feeling about this? Yeah, it's kind of like, this is a strange way of thinking. It's like, I'm not sure my brain was prepared for this. On a Monday after all this. On a Monday with the last 2 weeks of actual instruction. All right. If you have any questions, now would be a great time to ask them. If you are comfortable with this, give me a thumbs up. Tell me we're ready to move forward. All right. Moving forward. This is weird because this is one of the few formulas that I don't have on the poster. Like, I don't know what happened to my enthalpy poster. I might have left it in Spring Valley. But yeah. So this is one of the few really important formulas that's nowhere on the wall. So you just have to remember this or just put it there. Right on your hand. All right. So let's just sum up everything we talked about. A negative Gibbs free energy is a spontaneous, product-favored, energy-out system. Universe is like, yeah, negative delta G. Make it happen. A positive delta G is a non-spontaneous, reactant-favored, energy-required system. right now, I'm going to say pretty much all of you have a chemical reaction going on in your pocket or purse or backpack, hopefully in your backpack, that's doing this. When you take your phone and plug it in, you're going to be doing this. This requires energy. Recharging your phone, do you realize there's chemicals in your phone that are changing? Yeah. So a battery works. It's not like magic, like I get the magic from the wall and it goes into the battery where it's held, holding the magic. No, there's a chemical reaction going on. Right now, that chemical reaction is releasing electrons in a spontaneous process. When you plug in your phone, you're going to force electrons to move backwards in a non-spontaneous process. And if you get a delta G of 0, that's a situation we call equilibrium, which has its own unit that we're going to spend a week on.
Wow.
Yeah. Post-pandemic, woo-hoo. We used to do like a whole month on it, but we're going to spend 1 week on it. So if you have a delta G, that means neither the products nor the reactants are favored, and that is called equilibrium. Okay, that is that. So I'm going to move forward. All right, well, we can do some math too. We can start plugging numbers in. This is also a summary of what we talked about. Exo, endo, we're just ordering spontaneous, non-spontaneous. Let's do the math. Let's get to the math. All right. First and foremost, we do some math. If the enthalpy is non-spontaneous, but the entropy is spontaneous, what determines whether the reaction is spontaneous? Temperature. Temperature determines. So here we go. If a reaction has a delta H of positive 340 kilojoules per mole, non-spontaneous, and a delta S of positive 3240 joules per mole Kelvin, spontaneous. Is the reaction spontaneous at 470 Kelvin? Go.
Wait, would positive be? Wait, is the sign the direction of the heat?
I'm not sure what you mean by that.
Like, if we got a negative number, would that be?
If you got a negative number, then the answer to your question is yes. And we will volunteer our answers here in a second.
No, I'm just rolling with my. Because I went last year and all my things were right since I've been also
All right. Are we ready to move forward?
I didn't get it.
No complaints? No complaints. Okay, if you got a negative delta G, raise your hand. Uh-oh. Delta G equals delta H minus T delta S. The delta H is 340 minus T delta S, which is 470 multiplied by, what did I put in for delta S? 3.24. Once again, entropy is always measured in joules. Delta H and delta G are measured in kilojoules. So you need to turn your 3240 into 3.24. So that's about 340 minus, this is about 1400, if I remember correctly. It's about 1400. So it gives us a value of about negative 1100-ish.
Yeah.
The actual value is negative 1183. Okay, so the question that this asks is the reaction spontaneous at 470 Kelvin? And the answer is, yup. Yup. What about if it was, is it spontaneous at 50 Kelvin? See if it's spontaneous at 50 Kelvin. Exactly the same reaction. We chill it down with liquid nitrogen. Is it spontaneous at 50 Kelvin? Do you have an answer or a question?
Answer.
Yeah, let's let everybody else catch up. So at 50 Kelvin, the reaction is considerably colder, which means our entropy term is considerably less important. If you believe it still is thermodynamically favored, give me a thumbs down for a negative sign. If you believe it is now thermodynamically unfavored, give me a thumbs up for a positive sign. It is now thermodynamically unfavored, because when you take 340 minus 50 times 0.3 or 3.24, you get a positive number. That tells you the reaction is thermodynamically unfavored. Moving on. If a reaction has an enthalpy of negative 810 kilojoules and an entropy of negative 1524 joules per mole Kelvin, what temperatures make the reaction spontaneous? Your answer will start below this temperature, or all temperatures above this temperature. You have a thermodynamically favored enthalpy, a thermodynamically unfavored entropy. So since entropy is controlled by temperatures, your response will be below this temperature or above this temperature. Go ahead and figure that out.
But instead of really good, it's a bad.
It's a good thing we're taking
All right. Are you ready to move forward, or do you need more time? All right, a little more time. Take a little more time. I don't want to rush you. With some crusties and a lot of luck, you could look like me. Okay. First and foremost, if you got a temperature that is between 300 and 600, raise your hand. A temperature between 300 and 600, somewhere in that neighborhood? Uh-oh. Okay. Do I need to do this one on the board for you?
Yes.
All right.
I got it.
So we have delta G equals delta H minus delta S. So the point at which something goes from being spontaneous to non-spontaneous, or non-spontaneous to spontaneous, is what number?
0.
Yeah, the point between a negative and a positive is 0. So 0 equals negative 810 minus T, and the temperature is connected to the delta S times negative 1.524?
Yeah.
524. Is that math you can do?
Yes.
Pick your favorite arranging equation formula. What it ends up being is T is negative 810 divided by negative 1.524. Feels like 500-ish. 500, 532? 533? 531? 531? But it's going to be positive. Remember, temperatures cannot be negative. 531 Kelvin. So that is the point at which a spontaneous system becomes non-spontaneous, or a non-spontaneous system becomes spontaneous. That is the temperature, 531 Kelvin. Now we have to ask ourselves, the system says at what temperatures makes the reaction spontaneous. So our enthalpy term is spontaneous. Our entropy term is non-spontaneous. Do we want low temperatures or high temperatures? Think about it for a second. Take 10 seconds, convince your neighbor you're right. Our entropy term is non-spontaneous.
No, I meant like the
All right.
is
If you believe that we are looking for temperatures below 531, thumbs down. If you believe we're looking for temperatures above 531, thumbs up. Go for it. Thumbs up, thumbs down. Up, down, 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 up, down, up, down, 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 down. Looks like the downs are about 4 to 1, and it is down. We want temperatures less than the cutoff temperature because our entropy term is non-spontaneous. At temperatures below 531, your entropy term will be small, your enthalpy term will be big, and this reaction will be enthalpy driven. That's a lot for a Monday. Last question. If a reaction was found to be spontaneous temperatures above 1200 Kelvin and non-spontaneous below 1200 Kelvin, if its enthalpy is positive 852, what is its entropy? Go.
so well it would just make it 0.
That is the flipping point. The flipping tipping point is 1200 degrees. No, 1200 Kelvin.
Yeah, it's really bad.
Ben, what'd you get?
They have to be there. We want to Well, after 23%. There's 4 different answers.
What'd you get?
Well,
Want to see?
No.
Is that it?
Sounds like in the chat, are you ready to move forward? No? Okay, waiting. I'll give you a hint. The number is less than 1
Oh, yeah.
for the kilojoules.
Yeah.
And more than 500 for the joules. It's less than 1 for the kilojoules and more than 500 for the joules. Okay, so realizing the entropy should be in joules per Kelvin mole. If you got a number more than 500, raise your hand. More than 600, raise your hand. More than 700, raise your hand. More than 800, raise your hand. What did you get? 710 joules per mole Kelvin. 710 joules per mole Kelvin. So what you've got here is, once again, your delta G equals delta H minus T delta S. Delta G is 0 because this is the point at which the spontaneous become non-spontaneous, the non-spontaneous become spontaneous. Your enthalpy is a positive 852. Temperature is what we're going to be 1200, not what we're solving for. Temperature is 1200. And our entropy is what we're solving for, delta S. Add both sides. 852 divided by 1200 equals delta S. That appears to be 0.710. And that's kilojoules. So that's 710 joules per mole Kelvin. All right. Queries, conundrums. Shall we move forward? Question.
So would the to have a free energy of negative, that's thermodynamically favored, right?
Correct.
Okay.
Other questions? All right, finishing up. So, in summary, 3 concepts that you will be tested on Friday. Remember specific heat? MC. Did I put the formula in there? I did not. Okay, so the heat capacity when things warm up, MC delta T. Enthalpy, entropy, putting them together for Gibbs free energy. If you are comfortable with this and want to quit for the day, give me a thumbs up. If you want to chat some more, wave your hand around. All right. You can use the remainder of time on the attached worksheet.
You know when you guys like that.